I just wanted to do a quick walkthrough of what we've talked about in class the past couple of days, just to try to help alleviate any confusion that might have arisen. I'm going to start with the strong acid slide. Everything before this, I felt pretty confident that everybody understood, so I'm going to start here. And the first thing to know is that there's 6 strong acids, and if you memorize those 6, everything else is a weak acid. So when we talk about the strength of acids, remember, we're talking about dissociation. So if something completely ionizes, that would be a strong electrolyte, or in this case, a strong acid. So an acid that totally ionizes is a strong acid. And it's not in equilibrium. It's just going to go to completion. It's going to happen. But the weak ones are the ones that are in equilibrium. So when we compare strengths of acids, we're actually comparing the strengths of weak acids typically, because the strong acids are in a category of their own. So memorize these 6 strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. And if it's not one of those 6, you know it is a weak acid. Weak acids don't ionize completely. A lot of times, be prepared to recognize this notation with the HA and the A minus. The HA, of course, represents the acid. The A minus is its conjugate base. They go together. So we have our equilibrium going on here because the weak acids do not ionize completely. And then the equilibrium constant for that is the Ka value. So when we talk about the Ka value, the larger the Ka value, the further it's going to the products, which means the more of the ionized form is going to be in solution. So the more it ionizes, the stronger that weak acid is. So the larger the Ka value, the stronger that weak acid. And obviously you're going to leave out, in the expression you would leave out any pure liquids. So you'd end up with your H3O concentration times the A minus concentration all over the HA concentration. So in this case, which one's the stronger one? It is hydrofluoric acid, because it's got the larger Ka value, or the least negative of the exponents. So the autoionization of water, this is something that happens naturally. Water autoionizes by itself. So in other words, water will split apart into hydronium and hydroxide. It depends on which way you write it as to whether it's hydronium or just H+. Try to get used to using hydronium. That just means you're going to have an extra water on the left side. But mixed hydronium hydroxide, the water autoionization constant is Kw, and it is just an equilibrium constant for this equation. Notice that because we have pure liquids, and then the only thing that we can have molarities of are on the product side, you don't have like it over anything. It's all just the products multiplied by each other, so it's the hydronium concentration times the hydroxide concentration, and that is equal to Kw. That value is 1 times 10 to the negative 14th. So if you're looking at this equation over here, if Kw is equal to 1 times 10 to the negative 14th, in a neutral solution, these will be equal to one another. And if they're equal to one another, that just means it's a square root of 1 times 10 to the negative 14th. So that would be 1 times 10 to the negative 7th is the concentration of each of those in a neutral solution. This is also, if you're paying attention to the exponents, this is where we end up with the pH scale numbers. It's a 1 through 14 scale. Neutral is 7, which each of these would have to be 1 times 10 to the negative 7th in a neutral solution. So that's how we get those numbers. Since water is the only source of the ions, the concentrations of hydronium and hydroxide are equal and neutral when they are equal. So that is the ion product constant, and we call it Kw. So when you're looking at this, you can kind of use common sense. If neutral is 1 times 10 to the negative 7th, that means if you go greater than that for the hydronium concentration, it's acidic. If you go greater than that for the hydroxide concentration, it's basic, and vice versa. So in this case, since your hydronium concentration is 1 times 10 to the negative third, that means that it's greater than 1 times 10 to the negative seventh, so that solution would be acidic. So when hydronium is greater than hydroxide, concentration-wise, it's an acidic solution. The opposite is also true. If your hydroxide concentration is greater than 1 times 10 to the negative seventh, then it is a basic solution. So far, sorry about my numbers being off here, but this is everything you need to know. A neutral solution is going to have equal concentrations of hydronium and hydroxide. If it has more hydronium, it's acidic, more hydroxide, it's basic, and no matter what, the concentration of each, when you multiply them together, will give you 1 times 10 to the negative 14th. So if you have an acidic solution, that means the hydroxide concentration is going to go down so that when you multiply them together, you still get this. It's sort of like a seesaw. You get more of one, you're going to have less of the other. You get less of one, you're going to have more of the other. That sort of deal. So in this case, I'm not going to calculate the hydroxide. I'm just going to say, look at these. This one's going to be an acidic solution because it's greater than 1 times 10 to the negative seventh. This is neutral. This is basic because it's less than that. If you had to guess about the pHs, 1 times 10 to the negative seventh obviously is going to be 7. So you got the 7 here. But see, they're not always going to be 1 times 10 to the something. So if you had to guess on this one, you would say, okay, it's around a pH of 5. But there's more than just 1 times 10 to the negative fifth. So that's more acid, which means it would lower the pH a little bit more. So it's going to be between 4 and 5 pH. This one, it's more than 1 times 10 to the negative ninth. So it's more acidic than a pH of 9. So it's between 8 and 9 pH. You can guesstimate pretty easily with those. The pH, to calculate it, like we already talked about, take the negative log of the hydronium concentration. If you want to find the pOH, which we'll talk about more later, you take the negative log of the hydroxide concentration. If you add the pH and the pOH together, you'll get 14 plus pOH equals 14. And then remember also your hydronium concentration times your hydroxide concentration is equal to 1 times 10 to the negative 14. So what we have here, you can calculate the pH from the concentration, you can calculate the pOH from that concentration, you can calculate these from each other, and these from each other. So essentially, if you have one of those values, the pH, the pOH, the hydronium, or the hydroxide concentration, you can calculate the other three, which means there's going to be more than one way to solve a lot of these problems. I've already talked about that. We did those in class. You can do those to practice if you want. And then, of course, the pOH is basically the same. pKa, we'll talk more about this, but the pKa is just the negative log of the Ka value, the negative log of the acid equilibrium constant. And since the larger the Ka, the stronger the acid, the lower the pKa, the stronger the acid. A lot of times you'll see them reported in pK when you look up acid strength. So I think I'm going to stop there. I know that was very fast, but I hope that kind of helps us stay on top of everything. If you have questions, please just let me know.